Okay, this is part one of two talks about combination theorems for geometrically finite convergence groups. I'm Teddy Weissman. These two talks are going to be based on a paper that's joint work with Alec Traaseth. So in the first part of these two talks, I'm going to be talking about some of the definitions in the title of the talk. In particular, I'll be telling you what a geometrically finite group is, and I'll also be saying what a convergence group is and saying some things about how you can understand geometrically finite groups in terms of convergence group actions. So to get started, we want to be thinking about what geometrical finiteness means in a hopefully familiar context. That's two-dimensional hyperbolic geometry. So the object we want to start thinking about is a surface of finite type, meaning finitely generated fundamental group that has a complete hyperbolic structure on it. So I've drawn a cartoon of what this thing might look like down below. And so it is always the case when you have such a surface that you can find a family of simple closed geodesics. So that when you look at the core of this surface that you get by cutting off these complementary regions that are these tubes that you get, these tube components that you get by deleting these geodesics. The core of this surface, you can always write it as a union of some compact part together with finitely many cusps. So the compact part is this kind of blue region in here. And these cusps are going to be cut off, rather than being cut off by geodesics, they're cut off by horocycles. And like these funnels, they are also topologically tubes. So when you cut off all of the cusps and when you cut off these funnels, the resulting compact piece is going to be topologically equivalent to the surface that you started with. But the union of the compact piece, this blue compact piece together with the cusps, is always a convex manifold with boundary. I guess a convex hyperbolic manifold with boundary. Okay, so actually, what does that mean? What does it mean to have a convex manifold with boundary? Well, here's one way to understand this. So the fundamental group of this surface, which I'm going to call gamma, acts on the hyperbolic plane. And here's a picture of what the universal cover of, so that means that the hyperbolic plane is identified with the universal cover of the surface. These green geodesics, they lift to curves in the universal cover, and we can actually understand the universal cover of this convex core from this picture. So if I look at the limit set, which I usually denote lambda gamma, this is the set of accumulation points in the boundary of H2 of gamma orbits in H2. It turns out the universal cover of this convex core is going to be exactly equal to the convex hull of the limit set sitting inside of H2. And this convex core itself is the quotient of this convex set by this group action. So you'll notice the lift of these cusps are horovols in the hyperbolic plane. And so in the quotient, the quotient you might, when you quotient out this convex core, or rather this convex hull of the limit set by the action of gamma, the resulting surface, as we've already observed, is not compact, but somehow all of the non-compactness is concentrated at the cusps. So this manifold is topologically simple. We can understand it by looking at this compact piece, and this compact piece is this very nice convex hyperbolic manifold, and yeah, it only fails to be compact in this controlled way. So this is an example of a geometrically finite group. And this brings us to the general setup for the definition of a geometrically finite group. So the setup, we start with some complete, simply connected, negatively curved Riemannian manifold. The canonical example to keep in mind here is either real hyperbolic space or complex hyperbolic space, which is actually going to motivate a lot of what this talk is ultimately going to be about. I want to think about the group of isometries of this space. And I want to consider a discrete group, gamma, sitting inside of G, the isometry group of this space. I'm going to get lambda gamma, as on the previous slide, to note the limit set of this group. I'm also typically going to assume that gamma is torsion-free, although this is always an assumption mostly made out of convenience and not because it's necessary. It makes some arguments a little bit technically simpler. Okay, so the general definition that we're thinking about here, the group gamma is geometrically finite if the convex hull of its limit set modded out by the action of the group gamma can be written as a union of a compact part and finitely many cusps. So let's make a note that this is a finite set. So what exactly is a cusp? This is a little bit more complicated to define in this general situation than it was on the previous slide. But in general, what I mean by a cusp is just, it looks like a horoball, which is always something that you can define in any space X, like the one that I've taken at the beginning of this slide. I can take some horoball in the space X. I can intersect it with this gamma invariant set, which is the convex hull of its limit set. And then I can mod out this thing by the action of some parabolic subgroup. In my group gamma. And this is supposed to be the analog of the kind of cusp that I saw attached to my finite volume surface or finite type surface on the previous slide. So you want to think about geometrically finite groups as being the groups which are associated to quotients of this negatively curved space X by some discrete gamma, where the quotient has some nice topology. I guess nice or controlled topology. We don't want something that has like infinitely many ends or anything very complicated like that. And the goal for these two talks is to try and understand these groups a little bit more. Understand. And actually, the main thing that we want to be able to do is to give a recipe for constructing examples of new or interesting geometrically finite groups. And the main tool for both this talk and the next is going to be convergence group actions. So what's the deal with convergence group actions? The philosophy behind convergence group actions is that if you want to try and understand geometrically finite groups in this kind of context of groups acting on negatively curved Riemannian manifolds, you can actually get at a lot of the geometry by completely forgetting about it and only thinking about the topological dynamics of the group action on the ideal boundary of the space that you're acting on. So I will say a little bit more about what that means. But let me start with the abstract definition. So the setup, the context for where you define a convergence group is with some group of homeomorphisms acting on some compact metrizable space Z. Right now, we have no extra assumptions on Z, and we only know that gamma is just acting by homeomorphisms. It preserves no other structure on Z besides the topology. So I'm going to define this space Z, 3 parentheses. This is the space of distinct triples in Z. So to be precise, that's the space of triples Z1, Z2, Z3 in Z, which are pairwise distinct. That is, Zi is different from Zj if I is not J. And I'm going to say that my group gamma, acting by homeomorphisms, is a discrete convergence group if the action of gamma on this space of triples is properly discontinuous. Okay, so to motivate this a little bit, here's the canonical example to be thinking about. So if gamma is any discrete subgroup of PSL2R, and Z is the ideal boundary of hyperbolic space, of the hyperbolic plane, then this is an example of a convergence group action. In fact, you may be familiar with the fact that the action of PSL2R on the boundary of H2 is simply transitive on the space of triples. So if you have some discrete group going off to infinity, then your triples have to be collapsing in some way. You have this simply transitive action on triples in the space of the PSL2R action on the boundary of H2. But in general, you always have a properly discontinuous action, even when you look at the boundary of any negatively curved, let's say, simply connected Riemannian manifold. Possibly there are a couple of other technical adjectives that need to be added in order to make this true. But think about n-dimensional real or complex hyperbolic space as the example to keep in your mind. And in this case, I'm thinking about discrete subgroups of. It's an important adjective. I need to say a discrete group gamma in PSL2R, or inside of the isometry group of my negatively curved space X. Okay, so you can think of convergence groups as kind of abstracting away into the topology of the boundary, the notion of having a discrete subgroup of the isometry group of a space. You can sort of completely characterize the discreteness of the action on the interior just by thinking about the action on triples in the boundary. This is kind of a powerful notion, and maybe it's not so obvious why it's a powerful notion at first glance, but let me just point out that actually you can already see the limit set of your discrete group just from this definition. So you can actually define the limit set of any discrete convergence group to be the set of points Z in your compact metrizable space Z, such that you can find some triple x1, x2, x3 in the space of distinct triples, and some sequence gamma n in gamma, so that the sequence of triples gamma n x1, gamma n x2, gamma n x3 actually converges to some triple where 2 points are the same equal to this point Z. So if you think about it, the limit set of a discrete group acting on some negatively curved, some simply connected negatively curved Riemannian manifold. This limit set looks like places where points in the interior accumulate on the boundary, but it actually turns out to be completely equivalent to asking for places where at least 2 out of the 3 points in some triangle, the orbit of some triangle, accumulate to some point on the boundary. So you don't need to know what's going on in the interior at all to define the limit set. So it actually turns out that we can, in fact, even understand geometrical finiteness completely in terms of convergence group actions. So how does this work? Well, if you start with some geometrically finite group sitting inside of the isometry group of this Riemannian manifold, there are always going to be 2 kinds of points in this limit set, defined either via accumulation points on the boundary of orbits in the interior or via this definition via triples that I had on the previous slide. So there's one kind of point in the boundary, which is going to be one kind of point to the limit set, which is going to be parabolic. So these are the points circles. Okay. Okay. So parabolic points are going to be points in the boundary which look like the center of one of these horocycles or one of these horoballs, which is going to be whose quotient gives me one of the cusps of my quotient manifold. And what can I say about one of these points, one of these centers of horoballs? Well, first of all, I know that in this case, the stabilizer of this point z in my group gamma, it's infinite. And because it's a parabolic subgroup of isometries, it's infinite and it has a unique fixed point. I know that the stabilizer of z by definition fixes z, but I actually know that the unique fixed point of the stabilizer is z. And actually, because of the fact that my manifold decomposes into a compact piece, union finitely many cusps, it turns out that you can see that this stabilizer actually has to act co-compactly on the boundary of this horoball intersected with the convex hull of the limit set. Okay, so this property is a property of the action on X. It's not something that we can see by looking at the action on the boundary, but it actually turns out to have a consequence that you can see just by thinking about the action on the boundary. So the way to understand this is to observe that I have this co-compact action of the stabilizer on this horosphere here, or rather on the horosphere intersected with the convex hull of the limit set. But if I pick any point in the limit set, I can always draw a geodesic between that point and my fixed point. That geodesic passes through this horosphere somewhere. And actually, if I draw all of these geodesics for all of these different points and other different points in the limit set, I'm going to get roughly some kind of equivalence between these points in the boundary of this horoball intersected with the convex hull of the limit set, with just points in the limit set itself that aren't the parabolic point that I'm looking at. I have a kind of coarse equivalence between points on the boundary of the space and points on the boundary of the horoball. So you can actually see, as a consequence of the fact that you have this co-compact action on the boundary of this horoball, you actually get a co-compact action of the stabilizer of z on the limit set minus a point. So this condition is one that you actually can see just by looking in the boundary. You don't need to reference the interior of the space at all to talk about it. And this is what we call a bounded parabolic point. So specifically, bounded parabolic is this condition plus this one. Okay, so that's one kind of point that can show up in the limit set of this geometrically finite group. What do all of the other points look like? Okay, well, if you think about it, let me take any other point z in my limit set. What I can do is I can fix a base point x naught sitting inside of my space x. And I can draw a geodesic from x naught out to z. And now I don't know exactly what this geodesic looks like, but I do know one thing. I do know that this geodesic doesn't spend infinitely long in any one horoball, because the point z that I'm looking at is by definition not the center of any horoball. And if my geodesic just stayed in that horoball forever, the convexity would tell me that I would have to limit up to its center. So this geodesic might enter into a horoball. It might enter into infinitely many horoballs along its lifetime, but it never stays in one forever. It'll always leave. So that means I can find a sequence of points in the complement of all of the horoballs, inside of basically a sequence of points in the universal cover of the compact part of this of my manifold coming from this quotient of a geometrically finite action. And I can find the sequence of points along a geodesic limiting out to z. And because these live in the universal cover of the compact part, each one of them looks like roughly a translate of my initial base point, just because the action on this piece of the universal cover of the space is co-compact. So writing this out explicitly, for any of these points that are not parabolic, there always exists a sequence gamma n such that gamma n x naught converges to the point z along a geodesic in my space x. Okay, so once again, this statement, it only makes sense if you can reference the geometry of the space x itself. I have to be able to talk about geodesics in x, but there's a way to translate it into a notion that actually makes sense only referencing the action on the boundary. So the way to understand this is to think about the action of the elements gamma and inverse on the picture on the left here. So what happens if I do this? Well, when I apply gamma and inverse to this picture, maybe x naught goes all the way over here. But the point is gamma n x naught ends up, sorry, this is gamma n x naught, inverse x naught. Gamma n x naught gets sent to some point, my original base point x naught. And this green geodesic gets sent to some other geodesic, which passes close to my original base point in my space x. So my sequence gamma n doesn't need to preserve my geodesic, but it does take my original geodesic to a different geodesic, which passes close to some fixed base point. And the endpoint of that geodesic is gamma n inverse z. And I can also think about what this group element gamma n inverse will do to any other point, say a point y, in the boundary of my space x. Well, from the perspective of x, I can think about dropping a geodesic from y, like dropping a perpendicular down from y to this geodesic here. And so now if I think about where does y go, well, y actually has to end up pretty close to the backward endpoint of this geodesic, because if I drop a perpendicular from gamma n inverse y, that perpendicular has to be pretty close to gamma n inverse x naught. So what I conclude about the action on the boundary is that This point Z is what's called a conical limit point. Okay, what does that mean precisely? It means that there exists a sequence, gamma n, and distinct points, A and B, in the boundary of X, such that gamma n inverse Z converges to A, and gamma n inverse Y converges to B for any Y which is not equal to Z. So the idea here is because if gamma n inverse will, if I apply it to any point which is not Z itself, it'll always get sucked off to some point which is far away from gamma n inverse of Z. I can take the sequence gamma n that I had from this picture up top, and I can take a subsequence so that this sequence of points gamma n inverse of Z converges. And then I know that the backward endpoint of that geodesic that I'm seeing is where every other point is going to converge when I look at the action of the sequence of group elements gamma n inverse. And the point is that this definition of conical limit point, once again, you only need to reference the action on the boundary. You don't need to understand the action on the interior at all in order to make sense of this. So this is particularly nice, especially in view of the following theorem. So again, the setup, I have X as simply connected, negatively curved, complete Riemannian manifold, and a discrete subgroup of the isometry group of this space. Actually, this theorem that I'm about to quote holds in more generality than just thinking about negatively curved complete Riemannian manifolds. In fact, you can replace this with X being a delta hyperbolic metric space. But after all, this is the discrete subgroups of Lie groups section, so I think I'm going to mostly stick to thinking about things like symmetric spaces where the isometry group really is a Lie group. But in any case, in that context, the theorem, which is due to Beard and Maskett, and also, I guess, technically Bowditch in the slightly more general context, says that we have the following characterization of a geometrically finite groups. So a group gamma, this discrete subgroup of the isometry group, is geometrically finite if and only if, every point of the limit set of gamma is either a conical limit point or a bounded parabolic point. Where once again, these definitions, these are exactly the definitions that I've given on the previous slide. And the upshot is that this definition makes sense even if we forget the space X and only remember the action on boundary X by homeomorphisms. So in fact, you can take this theorem and turn it into a definition of geometrical finiteness for convergence group actions on compact metrizable spaces, and make sense of what it means for a convergence group to be geometrically finite without ever saying that it is the isometry group of some metric space. Okay, so that's the end of the introductory talk. In part 2 of the talk, the goal is to try and apply this theorem, to try and apply this characterization of geometrical finiteness to prove or to provide a way to actually construct more examples of geometrically finite groups given a pair of groups that you already know are geometrically finite. Great, thank you.